Hello, my name is Angelina Dominguez, and I teach AP Computer Science Principles at Veterans Tribute Career and Technical Academy over in the wonderful Las Vegas, Nevada. And I'm excited to be talking to you today about binary numbers. So let's see what we're going to look at. So today we're going to talk about how digital data can be represented using binary. We're going to talk about what binary numbers are and how binary helps us create abstractions. We'll look at what analog data is and how we use that to create digital data. So let's get started. So we've all seen computers, whether it's an actual computer, a tablet, or a smartphone. We've all seen them do crazy, miraculous things, things that seem like crazy things, right? With like pictures, graphics, sounds, you name it. You might think that displaying text on your screen or creating a picture or video is really complicated. In reality, it's actually not. In fact, all the wonderful multimedia stuff that we see on modern computers is made possible from simple on-off switches, millions of them, but really nothing more complicated than a switch. So all computers use something called binary. But before we talk about binary, I want you to think about a couple questions for me. First, what does the prefix DEC mean? Second, what do these three words have in common? Bicycle, biplane, and binoculars. And third, what is the symbol on most power switches? Maybe there's one on your monitor right now. So pause the video, think about those questions, maybe jot them down if you want, and unpause when you've got some thoughts going. Awesome, let's check out those answers. So the prefix DEC stands for or means 10, like a decade is 10 years. Those three words have in common the prefix bi, right? So bicycle, biplane, binoculars, they all mean two, right? Bi means two. So let's actually pause right there and kind of put a couple things together. So if the prefix DEC means 10, we know that the number system, called the decimal number system, that a lot of people use, uses 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. 10 numbers, 10 digits. So if that word, the decimal number system, has that prefix DEC, which means 10, let's try and apply that reasoning to the prefix bi and this number system called binary. How many numbers do you think the binary number system has? If you said 2, you are absolutely right. A 0 and a 1. Okay, let's look at that third question. What did y'all draw for the symbol that you normally associate with a power switch or normally see on a switch? Maybe you drew like a circle with a line in it, or like an almost closed circle like this with a line through it. That's interesting. We're going to come back to that in a second. So let's talk about this binary then. So binary, like I said, is a number system that uses two digits, 1 and 0. 1 represents an electrical signal on your computer being on, and 0 represents that electrical signal being off. So 1 is on, 0 is off. So you'll hear this term when we talk about binary, um, the term bit a whole bunch when you talk about computers, when you talk about binary, and bit is short for the digit or for the term binary digit. It's the smallest unit of data in computing. So a bit is either a single one or a single zero. And a byte is a group of 8 ones and zeros. So it's a group of 8 bits. So let's go back to that third question that I asked you a second ago. The symbol that represents the power on off switch that you normally see on when you turn things on and off. Look at that. It's a 1 and a 0. What? First time I recognized that, it blew my mind. So how does this relate to the physical processes of a computer? The circuits in a computer's processor are made up of billions of transistors. A transistor is a tiny switch that's activated by the electrical signals it receives. The digits 1 and 0 used in binary reflect the electrical signal being on or off. Everything in your computer ends up getting converted to this simple binary code that activates these electrical signals to tell the processor what to do. So all software, music, documents, any other information that's presented by a computer is stored in sequences of binary, in bytes of information, these ones and zeros. And how the binary sequence is interpreted depends on how it will be used. A binary sequence or a byte of data like 01001001 is used to represent instructions to the computer of various types of data depending on the context. So let's look at an example. What the binary data, the ones and zeros represent in a computer, again, depends on what is running on a computer. So for example, if I hit A on my keyboard, the computer sees 01000001. But what it does with those ones and zeros, what the output is, depends on what I'm doing. If I'm in a word processor, like Microsoft Word or Google Docs, it would show an A being typed on the screen. But if I'm playing a game on my computer and I hit A on my keyboard, the computer still sees 01000001. But since I've got a game open, it might give the instructions to my computer to move my player left. The important thing to remember is that the ones and zeros can really represent anything. Multiple types of data, including images, numbers, text, sound. The computer determines what type of data the binary sequence represents by the context in which it's used. So what's kind of cool is that no matter what data a binary number sequence represents, we don't have to worry about any of those details because of something called abstraction. Data, digital data, is represented by abstractions at different levels. An abstraction reduces complexity and allows us to focus on the main problem or idea. At the lowest level, bits represent all digital data, all those ones and zeros, those electrical signals moving through the processor. Again, luckily, we don't have to worry about how our computers use binary and the on-off signals in order to use them. Just like how you don't have to worry about, or you don't even have to know how the engine of your car works in order to drive it. Under the hood, there are all of these complex things happening with like the spark plugs and the alternator and the flux capacitor, but we don't need to know how any of that works in order to be able to drive the car. All we need to know how to do is put the key in or press the button nowadays, press the gas to go, brake to stop, turn the wheel to go to steer. All those other details are hidden so that we can instead focus on the main task at hand. This is abstraction. Abstraction reduces complexity and allows us to focus on the main idea or the main problem at hand. So let's look at a text message, for example. You and I type on the screen of our phones in alphabetic characters. Under the hood, our phones are actually seeing something called ASCII code, which are just codes or decimal numbers that represent text. So when we type hi, H-I, our phone actually sees ASCII code 72 and 105. Under that, our phones will turn those decimal numbers into binary ones and zeros like you see here, which the processors then of our phones will read as on-off signals. Images work much the same way. You and I see colorful, nice colorful images, but the digital image under the hood is made up of pixels, tiny dots on your screen. If you were to get a magnifying glass and put it up to your phone or put it up to your computer screen, you'd see little dots. Each dot is made up of a mixture of red, green, and blue colors. Underneath that, under the hood, each color channel has a value of 0 to 5, which tells the computer how bright to make the color, which is then converted by our computers to binary. And then again, the processors of our computers read those ones and zeros as on and off signals. So what did we do before our lives consisted of these ones and zeros? You may have heard of the term analog before. This is referring to things that are not stored digitally, but instead stored in physical mediums, like a painting or a record. However, there is now a need to turn things digital to preserve them or share them easier or send them easier from person to person. When we turn these things from analog to digital, this is where abstraction comes into play yet again. Think about a painting, an actual painting that you've seen. Think about what it looks like up close, the colors, the textures, the physical properties of the paintings. Many of these things don't get copied when we transform them into the digital form of the painting. Because all of these little details end up being hidden and they're not part of the bigger picture, the main idea of the painting, they end up getting lost. The use of digital data to approximate real world analog data is an example of abstraction. Now, it's important to try and maintain some of the details so that we can ensure the digital copy is as close to the real world analog as possible. Additionally, how do you represent smoothness of a piece of analog data, like a painting, with a simple on-off switch in binary? Well, for this, we use a technique called sampling. When we use sampling, something like a song or a painting, we measure the values of the analog signal at regular intervals. These samples are measured to figure out the exact bits to create the song and store the analog data in digital form. You can think of it like averaging or approximating. So we've reached the end already. What should we have taken away? So we hopefully saw how data can be represented using bits. We saw how computing devices represent data digitally using bits, using those ones and zeros. We talked about what a bit is and what a byte is. We also talked about this idea of abstraction and how abstraction hides the details, allowing us to look at the big picture, focus on the main problem. And we also saw how the same sequence of bits can represent different things depending on the context. We also looked at analog data and how analog data using a technique called sampling can be used to turn the analog data to a digital data format. And that's it for today. I hope to see you in the future. Bye-bye.